Come on, I'll get through this. Okay, I think this is the right one. Lecture 12. All right. Yeah, let's see. A few updates and stuff. Still working on the grading of your exams. Sorry, it just takes a while going through everything, and it's just a busy week with stuff. Everyone get a chance to watch the review of the review video and stuff. Still, if you go through it and stuff isn't making sense, I can walk through it a little bit more in detail. It's not a cumulative exam, so like this next exam is going to be based off of part 2 stuff, but PE, FE material like this these problems are very similar to that. Not as like comprehensive, but like little parts of it.
So starting from this question,
yeah. Sorry, I was scared. So what we're going to be covering today is lateral earth pressures. We already kind of introduced this a little bit in Geotech 1, but I know it's just like a little tiny aspect of it. So hopefully we'll be able to get into more detail for this. This is not right. That's old. What I did want to just update everybody for these next 3 lectures after today. They will be recorded, and so we won't be having class or in class time here. So at least for the 31st and the 2nd, there will be links. You guys can join live. This one I'm just gonna have to post. So this one I'll have posted. Like I'll probably post it tomorrow or something. So the notes for all of these should already be posted. But yeah, for October 31st, November 2nd, you can join live to ask questions. If not, though, it's okay. I'll post the lectures right after the class. All right, today we're going to be talking about retaining walls. This is a type of foundation technique, oftentimes in other states when we are building foundations, especially if we're needing to excavate, we're going to have to build some type of retaining wall. So in order to calculate the retaining wall, then we need to determine the lateral earth pressures. So this is that sigma H, the lateral earth pressure, or horizontal earth pressure. So remember when we did the whole like vertical, that would be our sigma V. Sometimes we just show this as sigma naught, which is the in situ total stress. And if you remember from geotech, the horizontal earth pressure is a function of this. So whatever the vertical is, an aspect of that is a horizontal. So as we increase the vertical, we increase the horizontal. But there's a certain factor. Who remembers what like letter we use to represent that factor? It's in the American alphabet. N? No. C. Yeah, K.
It's 3.
I don't know why we use a K. Yeah, so K is how we relate the two, and then there's different versions of K depending on whether the soil is moving, depending on the soil is at rest, or depending on if the wall is passively, all the stuff that we'll explain about here. But just, you'll see a lot of these Ks, there's different Ks, so keep track of which K means which and which equation relates to which throughout these next couple lectures. So where B is in chapter 11 and chapter 16 of these 2 textbooks. You can just Google horizontal earth pressures, lateral earth pressures, and I'm sure there's a lot of videos online that help illustrate this in a little bit more detail. So retaining structures, there's all different types of retaining structures, and for every single type, so these are just some cross sections, you're going to need to know the horizontal force that is acting on these. And the geotechs need to design this, and they also need to work with the structural engineers to ensure that whatever they're designing is also able to withstand the horizontal forces. So if you think about it, like this type is called a gravity wall. Gravity walls are just massive, large weights that are able to withstand any overturning. But in some cases, if we have pile or sheet walls, so sheet pile walls, like those super long ones, these are relatively thin And we would need to ensure that this type of material is able to withstand that loading. So we almost visualize this as a beam in some cases. So you could picture how if we tilted this whole thing sideways, the loading would look very similar to a beam. Other types that we have, this is called a cantilever. This is a really popular type because it's like a gravity, but we save in a lot of material. So for this type of wall, we actually use the weight of soil acting on these like little T shapes to withstand overturning. So you actually use the weight of that. These walls here, this is just a little schematic diagram of an MSC wall, which we've talked a lot about in Geotech 1. That's mechanically stabilized earth. So it's very similar to a cantilever beam, except we're using the weight and the friction of the soil on these tiebacks right here to withstand the horizontal force going sideways. The applications of these, they could be like basements, so actually creating your footing here, as well as retaining a wall. So again, everywhere except Florida, they do basements. Other things like bridge abutments. These are anchored to, so you can have other different types where these are called dead men, which is kind of fun. Or now they're probably called dead women too. It's 2022. There we go. No more dad jokes. And then tiebacks as well. This is another type. So you could teach a whole other class on retaining earth structures, all these different types of designs, but all of them need to include the horizontal earth pressure. So that's a function of the soil. So when you're doing your subsurface investigation, you're assigning the phi angle, you're assigning the cohesion factor, you're also going to be assigning that K value, which is the horizontal earth pressure coefficient. So the lateral earth pressure, this is well, first of all, there's 3 different behaviors. And there are 2 theories. So 2 ways of estimating these different behaviors. And there's lots more out there, but the most important ones, the ones that are used the most in the US are these 2 things. And on the bottom, you can kind of see the little fast forwards to it. The 2 techniques that we use are the Coulomb method and then the Rankine method. And just like everything else in geotech, I want to highlight the dates. These are very old, and they're all based off of like fundamental mechanical equations. So understanding how like free bodies, all that fun statics and mechanics and stuff, these are all based off of that. And then they're then related to soils. Now the 3 types of behavior there is at-rest conditions, there is active conditions, and there are passive conditions. So the lateral earth pressure on a wall restraining from moving. So if the wall is just standing still, there's no moving, it's just static, everything is static, then what we call is the at-rest conditions. So this is when the soil is hanging out, there's nothing like moving at all, at rest. Now there's 2 other conditions or 2 other behaviors. This is where the pressure, one of them is when the pressure on the wall tilts away from the restraining soil. This is the active conditions. So always think about this verb here. Is this verb actually? I don't know. Active, I don't know. Engineering, don't know what this is, but these words here, active, this is from the standpoint of the soil. So if the wall is tilting away from the soil, then that means the soil is pushing on the wall. So the soil is active, it's moving towards it. So this would be a common case here would be like if there's extreme loading here, like if we build a foundation right here. And this causes soil movement, and that soil movement wants to push on the wall. So the soil is actively pushing on the wall. The other one would be the pressure on a wall that is pushed into the soil. This is what's called our passive condition. So this is where the soil is not doing the pushing, but it is getting pushed on. So this one right here. This could be from something hitting the wall this way and actually pushing on the wall to push against the soil. It could be like waves crashing on the wall, something like that. It could, essentially where the soil is pushed upon. And these two guys, they found that in these three cases, the soil is going to behave separately. So we need to define this horizontal earth pressure separately in all three of these cases. So what they came up with are the horizontal earth pressure at rest, which is shown by a K naught or original conditions, K naught. And then following suit here, Ka is for K active or for active conditions, and then Kp is for passive conditions. So anytime you're doing a design, you need to first understand like what is going to be the critical state at which we need to design this for. If the soil is hopefully not moving at all, and K act or rest conditions, K naught conditions are going to be the controlling, then that's what we'll design the wall against. If you're planning on constructing something after the fact, and we know that it could be pushing against the wall, then K active. If this is like, again, like a retaining wall where there's the potential of like something hitting this, like a car or waves or something, and it's going to push into the soil, then you have to do K passive. So let's review this lateral earth pressure coefficient. So just like if you were in a swimming pool, if you go down deep underground or under the water surface or in a lake or something, you'll feel pressure, and that pressure is coming from the water, and that water is acting vertically, but it's also acting horizontally. So same thing with soil here. So if we have a horizontal or an in situ stress on just some random piece of soil, we'll also have a horizontal pressure. Now, unlike water, where it creates an equal amount of pressure, soil is an individual, like granule material that is affected by gravity. So the vertical is going to be different than the horizontal, or it can be different than the horizontal, I should say. So the way we define this K value, okay, I'm just going to put a box here because it could be active or passive or at rest. This is equal to the horizontal, or sorry, not the horizontal, other way. This is equal to the at rest or the original condition, sorry, not at rest, original, divided by the horizontal. And now since we're in geotech, what we do is these are always going to be effective stresses. So we take out the water. That's easy because the water is going to be acting the same. Like the pressure from the water in the vertical direction is the same as the horizontal direction. So that means we can find the horizontal or lateral earth pressure by multiplying whatever this K value is times the in situ vertical stress. And the in situ vertical stress, we should all know how to solve that by now, right? So in situ total stress minus the pore water pressure. So what's important here is that the horizontal earth pressure is always effective. So this would be in just like the in situ state condition. Of course, so you can see how if we use this in terms of a retaining structure, then if we have a little piece of soil right here, then it's going to have this sigma naught right here, but it'll also have a corresponding H as well. Oh, sorry. The horizontal earth pressure is always effective, so it's effective stress. So we know that this sigma H is equal to K times the vertical effective stress. And we know the function for vertical effective stress, if it's dry conditions, then this is just going to be gamma of the soil times H. So if we have a soil condition like this, where everything stays the same, so our unit weight is the same, and our K is the same, then what we would expect to see is this profile of stress be higher at the bottom and then 0 at the top, right? Because at the top, there's no overburden. So we can get a stress profile acting on this retaining structure. And if you tilt your page over, you know, and draw this as like a beam, then you can see how it just looks like a triangular distributed load, right? So that's where we have to unfortunately go back to statics or structural engineering, and we can calculate the resultant force, which is used for design. Right? And how we show this usually is as a P. So this is the resultant force P. Yeah.
I have a question. Maybe I didn't follow. Is it the sigma H? Does the equation come from the equation, or is it a different one? Does it come from the one on top, or is it a different equation?
It is.
Box?
Yeah, it's Did you that wrong?
Yeah, it is. I would agree on that because if you're solving for sigma H, then it would be sigma 9 over K.
Yeah, no, you're right. Good catch. That one is. Why did I get that mixed up? This should be the other way around. Or sorry, KH. Yeah, your sigma H should always be less than your sigma vertical. Sorry, good catch. So what this should be is our K value is equal to sigma H divided by sigma vertical. Yeah, that's right. So and try to think of it like well, I guess it could be potentially more. Most of the time, the horizontal pressure acting is going to be less than the vertical acting. So most of the time, these K values are going to be either 1 or smaller. They could be higher than 1, but most of the time they'll be either 1 or smaller. So if it was smaller, yeah, it would be that way around. Yeah, so what we would show this then is like this blue, so this would be the stress profile, and that would be important. But then we would also need to find the resultant force. We know if it's a triangle, that's occurring 1/3 of the height from the bottom. So the typical lateral earth pressures at rest, these are just some of the examples here. And we'll go through some of the equations of how we find these. But if we have saturated loose sands, this is like 0.46, saturated dense sands, 0.36, dry loose sands, 0.65, dry dense sands, 0.49. These are some of the ranges. An equation that we use for sands. It's this one here, K naught is equal to 1 minus sine of the friction angle. That's one of the correlations that we use for that. And remember this equation here, this K naught, the higher the number, then the closer the horizontal is to the vertical. This should be so loose sands, loose material is going to be a higher value. It's going to exert a higher amount of horizontal pressure than dense material. So that's one of like the things that could be a little hard logically to grasp. But the reason for that is because of soil arching. So if we think about it, like if we had a little pile of sand and it was in a low density, so if you just like fan it, you know, down and you're not compacting it, then it would want to spread horizontally, right? A loose material will want to spread horizontally. Where if we had sand and we were compacting it, it would not want to spread as far horizontally. So a higher dense sand, more of its weight will be exerted vertically instead of horizontally. So that's why we see for the loose materials, we have these higher numbers. That's just usually the denser the material or the higher the friction angle is, the lower the number. For clays, compacted clays, there's a bunch of different equations. 0.42, these are usually a little bit tighter, 0.42 to like 0.57. These are some of the examples. This guy, these two guys, Paul Main and Kulawi, they have a big manual that if you get into geotech, they have a lot of soil parameter correlations to different tests. These two guys out of Georgia Tech. They use this equation, or they introduced this equation, I should say. Where they use a function of the OCR and the friction angle. So it's OCR to the power of sine times the friction, or sine of the friction angle. So that's one of them that you can use with clays. There's a lot of empirical data coming out too as we're collecting more data and doing tests to actually find the K naught values. Then you can start getting more empirical relationships. So I should say these are at rest, which means this is K naught. So this is not something you would use for K active or passive. Those are different theories. So these are at-rest conditions for a dry backfill. As I mentioned before, if this had a height h, we know right here we would have sigma naught and a sigma h. The resulting stress profile would be just a simple triangle for the stress profile. So from that, we could find our maximum or just our function of this stress profile. Through the following equation. This would be the at-rest earth pressure coefficient. And since we have dry backfill, which means there's no pore water pressure, that means our total stress is equal to our effective stress. So then just find it by knowing the unit weight times the total height, right? Or however the depth is. So that would be this point right here. So what we're assuming is this is homogeneous material or homogeneous soil, meaning that there is one unit weight and there's only one earth pressure coefficient. If you have different layers or stratigraphy, then you would have to do a different profile, right? Each little triangle would be a different slope depending on that. So I mentioned some of the other ones previously, but just to, here, let me show this then. So yeah, this would be the stress. We could also show the resultant force of the at-rest condition by just assuming this is a distributed triangular load. And that we show as a P0. So our at-rest resultant force. And that's just the area of the triangle. So that would be K0 times H squared. The reason how we get this equation, again, is just the area of the triangle. This is the point times the height, so the height versus the base, I guess, and the base is H. This is equal to K0 gamma H, so that's why we have the H squared, and then 1/2 base times height, that's why the 1/2 is there. I showed these before, but just to define some of them. The ways of estimating the K0 value that we used, I don't know how you pronounce this, Yakis maybe, just because I don't think his name is Jakey. This is from 1944. This is the most common one for granule or just sandy soil only. That one there. Main and Wally, spelled that wrong. This is from 1982. This is an update to it. And then the other one here, Orange, 1979. This one is an empirically based, which is why the equation is just a simple like statistical regression. So you'll see there's a lot of other equations. These are some of them you can use, but it's always going to be based off of what data you have available. So PI, that's the plastic index. Remember that one? Remember the cup, the Casa Grande cup, and how super precise that was. So if your data isn't like, if you're not super comfortable that your Casa Grande cup data is really accurate, then probably should stray away from this equation. Likewise with the friction angles. If you're correlating to find the friction angle, and then you're using a correlation of a correlation, then that can be bad sometimes too. So it's all dependent on how accurate and how confident you are in your data itself. So as we have different types of scenarios, like say we have a surcharge or some type of loading on top, then this will also affect the horizontal earth pressure as well. So this is really common, especially because a lot of times these walls are going to have some type of other type of infrastructure on top, like a roadway or an existing building or something along those lines. So whenever we're doing that, since it's still a dry backfill, we would still have the same soil profile. Let me just draw this. It only goes to the extent of the wall. That's what we care about, at least. We would still have the existing from our soil profile right here. Where this is going to equal K naught times the gamma H as the max. And we would do the same thing as before, since this is a stress profile, all that fun stuff. We could find the resulting force from this. I'm just going to draw it in orange here. So we could find our resulting force. But if we have a surcharge, let's just call this surcharge has a force or stress Q. So like, for example, like if it's a roadway surcharge, you usually do 150 tons per square foot for a Q. Like that's like, there's different standards that you'll come across based off of this. What we assume is that just for the height of this wall, we know that this stress, like using the 2-to-1 method or one of the boosted nest methods, this surface stress is going to dissipate with depth, right? But since this height of the wall is usually only, 30 meters, like 10 meters or so, like relatively small, what we assume to be on the conservative side is that this stress, this vertical stress, is being felt all the way down, the same amount. So that means if we were right here, we would still feel Q, the full brunt of Q. If we were right here, we would still feel the whole brunt of this surface loading. If we were here, we would still feel the full brunt of that surface loading. So that makes it easier for us because when we're drawing the stress profile, we don't see an increase like this and we don't see a decrease because it's not dissipating with depth. What we see is a constant stress being felt on the wall. So this, when we draw as constant, is just a rectangle. So instead of a triangular distributed load, we just have a normal distributed load. Now this normal distributed load, this is going to be the entire Q. So Q times K naught. And as long as the soil is homogeneous, which means we have consistent unit weight and consistent K naught, then we can just draw a consistent profile like that. Now we need to, when we're talking about structural designs of the retaining wall or the actual earth pressure on the retaining wall, we need to include both of these. So that's why what we'll show is this entire stress is equal to, we can bring the K naught on the outside since it's equal to the same. It's equal to the surcharge times the part of the soil. So anytime you have loading on the surface, we also need to multiply that by the earth pressure coefficient to determine the horizontal load. So with this one though, the resulting force, let me try to see if I can draw it. The resulting force here is acting in the middle, right? So that means this is acting H divided by 2, so halfway up the wall. This one is acting H divided by 3, a third way up the wall. So it makes the statics a little bit harder, but we can still find the result in that way. So who remembers, like, how would we find the resultant force here? Or the resultant, like where the location of the resultant force is? What was that? So I mean, it makes sense that it would be between them somewhere, right? But if this had a super high magnitude and this had a really small magnitude, then it wouldn't be exactly in between, right? So it's exactly like if we're trying to find the reaction force on a beam. Yeah, exactly. Yeah, so you would just take the moment around any point in the beam that you want. So let's just say right here, we'll use the same like statics terminology. So A, so we'll just take the sum of moments around A, and we know this is equal to 0, and we set a positive direction or whatever, just like we would do in statics. Now you have these two known, and we know that there should be a resultant force. I'm just going to show the resultant like somewhere between them. And then what you would do is you would just say that this is some distance that's unknown z between the two. So you would solve that, and of course, though, we don't have a value that is known for this, right? Like this would be known, this would be our, let's say, we would know this P naught, we would know this P naught, but we wouldn't know this one. But we would still use statics. We just use the summation of forces of the y direction, or the x direction is equal to that. So we could find the magnitude of this, and then using the statics, we could find the actual location of this as well, so the resultant. So oftentimes in geotech, like there's going to be different layers. So knowing how to do this for different layers, you might have more than just 2 horizontal earth forces. So we can find the P naught, the overall, by just adding these 2 different ones. So P1 plus P2. That's why sometimes you'll see these, especially if it's surcharged, you just add the 2 together. This is to find the location. Find location Z. And so we're not going to cover this in this class. Again, this would be like a grad level or like a design, another tech elective. Once you have this P naught, you would then look at the structural like integrity of our retaining wall itself. Retaining walls, you obviously don't want the soil to bend, so you would look at the deformation diagram and you would literally draw and do all those fun things from your structural analysis class, where you would actually have like a deformed shape or something, and then you would have to calculate this maximum deformation and make sure that this wall is structurally rigid enough so you don't have that maximum deformation, or that maximum deformation is acceptable, because if you have settlement horizontally, then you're going to have settlement vertically as well, right? Because if the wall moves out, the soil moves down. So anything on top of the soil is bad. Also, that's how you go from an at-rest condition to an active condition. So that could also be bad. So the other cases, so this is again just dry soil, single layer, dry backfill with a surcharge. So layered backfill with water, this could also be like something that's really common. And the whole thing that this changes, obviously, like we'll still say this is homogeneous soil, so we'll still say that, let's just say that our at-rest earth pressure coefficients are the same. But above the groundwater table, we'll have a certain unit weight, either dry or moist conditions. And then below, we would have saturated. So if we were to draw the earth pressure profile, the at-rest condition, just make sure I didn't have that. So I'll just draw these lines so I can try to keep it somewhat straight. So if we were to draw the at-rest earth pressure or lateral earth pressure, this top condition, if we just assume it's dry, then we would have something like this, right? Where this value would be K naught times unit 1 times H1. We would need to separate this into two separate heights. So we'll just say this is H1. H2. This will be our total H. So we would have this condition, and this is only from the soil itself. And now with this water, the water we know will also produce a consistent stress down. This pore water pressure will create a consistent stress. The way you can kind of picture this is like, if we view this second layer as having a surcharge on top of it. So just picture that this second layer here is just being treated as like this first layer, that's dry soil. This is just a surcharge on top of it. Then we know that it will have a consistent value underneath this right here. And so that's from the first layer. Of course, we have at-rest conditions here from the soil moving down further. So we should use a different color. Also, since it's a different K, it'll probably be a different slope, but this would be from the second soil condition. So this here would be from K naught H2. So since this is underwater, we use the submerged unit weight. You guys remember what the density is, or how we find submerged unit weight? So gamma effective or gamma sub. For effective stress, what do we subtract out of the total stress for water pressure? So for this, if we have our normal unit weight, what do you think we subtract out? Yeah, exactly. That's how we would find our effective, or what's just known as the submerged unit weight. So that's this addition right here. And then below we still have, just add this. Right here, we're still adding the condition from the top. So that's our K naught times unit weight times H1. So since our K naught values are for effective stress, anytime we're using our K naught, this will always find the effective stress. We know that since there's water though too, this water is going to exert a stress on the profile of it. So we can also find our pore water pressure, the profile of the pore water pressure on our wall. We know here it's 0, right? Because right where the water starts, and then as we go down here, we see a steady increase in pore water pressure. This is just the unit weight of water times H2, since that is the height of the wall that's underwater. Now, question for you guys, like just think about, like when we're designing a wall, what type of stress do you think we care about? Like what would be the stresses, like structurally, that we care about? Think about like the different types of stresses we've talked about: effective, pore water pressure, and total. Total, right? Yeah. So just to recap, geotech, we design for effective stress, because most of the time when we're talking about vertical effective stress, that is going to be lower than the total effective stress. The total stress would produce higher strength values, because again, like soil is frictional, so the more we press on it, the more strength there is against resisting, the more we press on it. So that's why most of the time we'll factor out the soil or the water, because the water can't be trusted. Like that leaves, and then we thought it had more strength than it didn't, but now it's looser. But for a wall itself, like we care about the total pressure. You know, like if it was just me pushing on this wall and there's pore water pressure behind me, but even if it leaves, then the pressure is going to be less on the wall. So when we're designing for the worst case scenario, we'll always design it for the total stress. So to find our total stress, then we would just need to add all of these together, because we know that the effective is equal to the pore water pressure minus the total stress, or total stress minus pore water pressure. So in order to get this, we actually need to add these two to get our total pressure. So we would have the same thing as before, but we would just be adding these two. So you would have this one plus these right here, and that would equal, sorry, I drew that wrong. So yeah, this whole point here, I'm just going to draw this here. Let's say this is point C. So at point C, we know that Z, so the total depth is equal to H, which is equal to H1 plus H2. So for the effective, or so the pore water pressure, we'll do pore water pressure to start because it's the easiest. This is just the unit weight of water times our H2 at point, or I guess that would be, yeah, at point C. The total stress would be the unit weight plus gamma saturated times H2. And the effective, sorry, these are verticals, so these are the vertical ones. So the effective would be plus the submerged times H2. So when we are finding our sigma effective horizontal, then we would multiply this by K naught. But then once we find our effective earth full pressure, and we find our total earth pressure by adding these two together. So the way to think of this is like this K naught value, this is the only translation from vertical to horizontal when we're talking about the effective stresses. So like we have to go through the K naught through effective stresses, but then whenever we design, we would usually then solve for the total stresses acting on the soil. I would draw on that a little bit better. I think we can show an example of it, but. So, like for example, then for this, like finding the resultant stress. I'll just try to color coordinate it here. We would have a resultant stress here. This, just say this is P1. We would have a resultant force, our resultant force here, P2, and then we would also have the resultant force here, P3. And then we would also have the water, P4. So when we're talking about this, this would have all of those combined. So you would add all of those up. So water will complicate things. And this is, sometimes you will design, like if you're having like a seawall or something, but a lot of times if you are building up, the goal is you would set some way of making it so groundwater doesn't accumulate behind your wall. So that's kind of like to help benefit that. Obviously, if you're by a river and you're drilling a sheet pile and putting a bulkhead by it, then you can't do that because it'll just, the river is going to keep replenishing it. But a lot of times we'll try to do some type of thing, either weep holes or there's like little holes on the side of the wall to like help water drain out, or some type of like aggregate or drainage filters to allow the water to like, so it doesn't build up behind the wall like that.
Oh, okay.
Yeah.
Whatever I understand. What's the difference between, like, why do we have to calculate the submerged density? Because isn't the submerged density just the same as the dry density without the water?
Yeah.
And if we have the water, so if you have a whole separate diagram there for water, why do we still have this submerged? Shouldn't all that be flat on the earth diagram?
Yeah, you could, but if you included this, if you used them saturated, then yeah. So
Can we just use all dry density? Doesn't it be one giant black triangle? It's really
oh, I see. Sorry. So this is the submerged is the saturated minus the unit weight of water. So you would have a different, this value would be different than this value.
Saturated. Why is it submerged? I guess my question is, why is submerged different from? So why is my submerged density different from my dry density?
Because the dry density.
I understand water, but we counted the water in the second column.
Yeah, that's the pore water pressure for this. So
Right. I'm sorry. Yeah. I get that part. I get there's two different things. But if we're accounting for the water in the second column, why do we have water in the first column also? I guess there's probably some simple answer no.
So let me try to explain it this way. The effective stress, this first column, this is essentially like what the soil is contributing to the soil itself.
Okay.
So the soil, when it's submerged, it has a lower weight. It's like a buoyant, essentially. So, but that like particle is pushing up against the wall and creating this P3. So that's only from the soil's point of view. So you're right, like to get the total, you just add this in. So this is soil only, this is pore water pressure only.
Right. So
So
I guess my guess is why is that little triangle still green if I subtract the pore water pressure? I guess it's mine. Like, isn't, I don't know, I have a hard time conceptualizing what's going on. So I have water sitting in that bottom half.
Yeah.
And that water, the saturated soil is going to behave differently than top dry soil.
Yeah.
I get that. But I'm subtracting I'm adding the pore water pressure in that second column. So I don't understand why I'm counting, it almost like I'm counting the water twice.
there's no pore water pressure in this one. There's no pore water pressure. So you're right. Like if we combine these two and just did K naught times gamma saturated times H2,
Right.
then no, actually that wouldn't be true because the K naught value is not acting on the water. So you have to separate the two because K naught is only for soil. So the K naught is only acting on soil. So that's why we need to have it separately. And this green triangle is only attributing from this right here. So like if we were to just cut off this top layer, if we were just to cut layer 1 out,
Right.
then that green would be the only profile we have there.
Okay, so is that green slope always going to be less than the top slope?
It depends on the K naught value. Yeah, it depends on the K naught value. Yeah, let me, you might just be like thinking of it like more logically, like this is just illustrating that there's two separate parts, you know, but you're probably combining it like and thinking that, okay, like, yeah, obviously there's water and soil being pushed on that.
Right, I get that. It almost seems, I guess my brain is not as, there's some disconnect in my brain. Because I see that you're taking the water out on that second column, yet I'm treating the soil, that green part is the soil water in. You see what I'm saying?
No, there's no, you're not treating, there's no water in this part.
Right, so why does it behave differently than the top?
Than this?
Yeah. Why does that green, if I'm subtracting the water out, why is it behaving differently than the top portion that's dry?
It's because the unit weights are different.
And the unit weight's different because, I guess, so
Yeah.
why is my unit weight differently if I'm taking the water out?
So the essentially like, you know, things have perceived weights that are different underwater than they are above water. So that's, yeah. Like this, let's just use numbers. Like let's say this is a dry unit weight at the top, and this is equal to like 100 pounds per cubic foot. Like if we took this same soil and put it underwater, it would have a perceived density that is less. It would be 100 minus 62.4, so 32. So that's why we separate them here.
Okay.
Now, the other thing I could say too is like, and hopefully this doesn't add too much confusion. We've seen these plots before, but it's always been vertical.
Right.
So when we're talking about vertical like stress and plotting the vertical stress, then we can usually just combine these two. We just use gamma saturated, and that's what these would do. But we can't do that when we're doing horizontal earth pressures because of this K value. So the K value is acting on soil only. The K value doesn't act on water. So that's why we have to separate the two.
I get it now.
Okay, cool. Yeah, well, I'll find a good example. We have an example here, but I don't think it's layered soil, but for next class or separately, I'll try to find a good one that has layered soils, and maybe the numbers will actually help a little bit more. Okay, let's knock this example out, and then I think that's it, yeah. All right, so we're told that we have a gravity retaining wall, it's 5 meters high, holds back soil. We're asked to find the lateral earth pressure per meter length of wall. So this is really common when we're designing. We usually just design for an idealized or worst case section of a road, you know, like it's for a whatever. If we have like a mile or a kilometer long wall that we need to design, we would find the different soil cross sections that are the worst case, and we would just design the whole thing for that, you know, just to save with unless the project's really long and it's like a design build or something. But so we'll design this per meter length of wall. So coming out of the paper, we're told that the soil is cohesionless, has a friction angle of 30 degrees, and a unit weight of 18 kilonewtons per cubic meter. Assume there's at-rest conditions and no groundwater table. So that's nice. So that means we're going to be using K0 only and no groundwater table. That means we're just going to assume gamma dry, since there's no moisture conditions given to us. We're also asked to determine the resulting force. So how we would draw this then, we'll draw our little wall. So gravity wall is just a big old block thing. Usually made of concrete. We know that the unit weight is 18 kilonewtons per cubic meter. Our phi angle is 30 degrees, and our cohesion is 0. So we aren't given a K0 value, so we need to find K0. So this is where you would look through correlations. There's tests that can find K0, so sometimes you can find it yourself. But for this, we'll just use our good buddy Jakey, or whatever his name is. K0 is equal to 1 minus the sine of our friction angle. So we plug this in, 1 minus sine 30. We see that this is nice and even of 0.5. So this is our K0 value. So that means that as our vertical stress increases, as we go deeper down, our horizontal stress is going to be half of our vertical stress. That's like what that is physically meaning there. So if you're not confident with this, then what you could do is first draw the vertical stress profile. And then once you have the vertical stress profile, you just multiply it by 0.5. Or you can combine the two. So what we'll do is say that's our stress profile here. So we know at the base, this is going to be equal to, don't break. Okay. This is going to be equal to our sigma H here, which is going to be K0 times unit weight times height. And our height is 5 meters. So again, hopefully you can recognize that this is just our sigma V, or our vertical. That's where we're getting that from. This is an H. So we'll plug all this in, 0.5 times the unit weight of 18 kilonewtons per cubic meter, and then times 5 meters. And that should be 45. So this is 45 kilonewtons per square meter. That's looking at this cross section only. Again, what we're saying is that it's coming out of paper, right? This wall is coming in and out of paper. So this is technically kilonewtons per square meter per meter length of wall. So in this case, there is no groundwater condition or anything. So this is also equal to our total stress, our sigma H. So this value would be 45 kilonewtons per cubic or per square meter. So we're asked to determine the resultant lateral force applied to the wall. So our lateral forces would be a P naught. One half. Sorry. Force. So the different equations, I'll just write both of them here, but I'll show like you can recognize. This is sigma vertical times H squared. The other way of showing this is one half sigma times 5. So this is kilonewtons per meters squared and then times meters. So it's kilonewtons per meter length of wall, or kilonewton per meter of wall. This is what then? 100. 12.5. Again, this reason this is coming here because this is unit weight times. Sorry. Oops. I wrote all that down wrong, sorry guys. So K naught times yeah, so this is the breakdown here. So this equation, I've shown it in a couple different ways. The easiest way to remember it is that it's just the area of the triangle, right? So if this is our horizontal earth pressure, then base times the height divided by 2. But then how to actually get this value down here can be shown in other ways. So that's where this is coming from. P naught, we just do it in different colors so I don't have to erase everything. P naught is equal to 1/2 times K naught times the unit weight times H squared, which is also equal to 1/2 Right, you guys remember this kind of from Geotech 1? A little bit of it. Okay, FE, there's definitely always gonna be a problem on this for on the FE. So yeah. Yep. Yeah. So that's why I'm drawing it here. It's at the bottom. So the deeper we go, the higher that H is, then yeah, the larger that value is.
So the PO, then.
The Q naught in those examples, that was when there was a surface discharge. So that's only when there's a loading at the surface. Oh, PO, sorry. PO, this is the resultant force. So this is a strength profile. So just like if we were doing a beam or something right here, and we had a distributed load acting on this beam. In statics and stuff, you showed this as like a W, right? The resultant force would be W times L. That would be the resultant force. So same thing, you're just tipping it over. And now this H or this L is an H. All right, disappeared. The L is an H, and the distributed load is the sigma H.
Well, I figured out. I was wondering why it was H squared, but it's just the gamma H from the sigma.
Yeah, yep, exactly. They put that into that. Yeah, so the active earth pressure here, this is, or sorry, the passive K knots. This is kind of, I don't remember who came up with it, but then once you start looking into active or passive, it's the same thing, but you're just changing this value, the K value. So you'd still draw the same profile, but this K value would be separate. And so that would mean if your K value is different, then your stresses are different, which means your horizontal stresses. But the important thing that Cullum and Rankine did, they also looked at if it's passive or active, then that means the soil is going to be moving, right? Either the wall is moving out or the wall is moving in. The soil is going to be moving. So the angle at which the soil is moving is important. And that's like where we'll kind of catch up on in the next class. So yeah, that's it, guys. We'll recap this. I'll try to include some examples for everything. Groups, have you guys at least seen who's in your groups and stuff? Okay, cool. So you can, if you need help picking a topic, let me know. I can assign you one, but I will see you guys in November, I guess, in 2 weeks. Yeah, no more class.
Have fun on the beach.
Yeah, the beach. Right now. Going as far from the beach as you could possibly go.
Yeah, I'll get
Oh.
You are. Usually it's a 4, but I'm kind of.
Their idea.
I'm just gonna be sitting at home.